Dear students, today we are going to discuss about the geometrical optics analysis of optical resonators. So let us consider a spherical resonator bounded by two mirrors of radii of curvatures R1 and R2 as shown in this figure. Here M1 and M2 are two mirrors of radii of curvatures R1 and R2, and they are separated by a distance small d. For resonators having larger Fresnel numbers, the loss occurring due to diffraction is small, and the resonator can be studied using geometrical optics with the help of a matrix treatment, since it is suitable for the study of ray propagation in an optical resonator. And we will obtain the condition to be satisfied by R1 and R2 and D so that the resonator is stable. In a stable resonator, a ray of light may keep bouncing between the two mirrors indefinitely. Because of the periodic focusing provided by the spherical mirrors. But in an unstable resonator, the ray escapes from the resonator after a few to and fro travels. So let us first obtain the matrices which represent the propagation of a ray through a homogeneous medium and the reflection of a ray from a concave mirror. So for that, let us consider the second figure here. The ray is propagating in a homogeneous medium in the xy plane. The ray may be described by specifying the height of the ray, that is the x coordinate, and the angle it makes with the z-axis, namely theta. The z-axis is assumed to be along the axis of symmetry of the optical system. For a simple mirror, it is along the axis of the mirror. Here we are considering only the rays which are traveling close to the z-axis and which do not make large angle with it. And so we can say, under this approximation here, x and theta, under this approximation both x and theta are small. And so we assume that sin theta nearly equal to tan theta, which is nearly equal to theta. Okay. And from the figure we can write, let x1 and x1 dash, which is equal to dx by dz, be the position and slope of the ray at a plane z equals z1, and slope of the ray at a plane z equals z1. Then the slope of the ray at any plane z equals z1 plus d, lying in the same medium, is x2 dash equals dx dash by dz at z1 plus d, which is equal to dx by dz at z equals at z1 equals x1 dash. Also x2 equals bq, which is equal to bc plus cq, which is equal to bc equals AC tan theta. So which is equal to AC tan theta plus CQ. So here from figure CQ is same as AP. So we can write it as AC tan theta plus AP. But from figure, AP equals x1 and AC equals D. Therefore, tan theta equals slope, which is equal to x1 dash. So, x2 equals AC tan theta plus AP. That is, thus we can represent the initial ray by the column matrix x1, x1 dash, and the final ray by the column matrix x2, x2 dash. Then we can write x2, x2 dash equals 1D 0 1 into x1 x1 dash. Let this be equation number 3 here, that is by matrix multiplication. We can write x2 equals 1 into x1 plus d into x1 dash. It is same as equation 2, that is x1 plus dx1 dash. And also we can write x2 dash equals 0 into x1 plus 1 into x1 dash, or it is written as x2 dash 1, which is same as equation 1. Thus the coordinates of a ray at a plane can be found from the coordinates of the ray in a previous plane at a distance d by multiplying with the matrix T, which is equal to 1D 0 1, and this matrix is called as the translation matrix. And it represents the effect of propagation through a homogeneous medium of length d. And the determinant of this matrix T, that is determinant T equals 1D 0 1, that is 1 minus 0, which is equal to 1. So let this be equation number 5. Now let us find out the matrix which corresponds to the reflection of a ray from a concave mirror. So we are going to find out the matrix which represent reflection from a concave mirror. So for that, let us consider this particular figure. Now we are going to find out the matrix which corresponds to the reflection of a ray from a concave mirror. Let the coordinates of the ray be x1 and x1 dash. Before suffering reflection from a mirror of a radius of curvature r, we have to find out the coordinates of the ray just after reflection. And it is clear that the reflection from the mirror only changes the slope of the ray. Its position coordinate remains the same. Hence we can write x2 equals x1. In order to calculate the slope of the ray after reflection, we use the mirror equation 1 by u plus 1 by v equals 1 by f, and we know that f equals r by 2. Therefore, we can write 1 by u plus 1 by v equals 1 by r by 2, or 1 by u plus 1 by v equals 2 by r. Let this be the next equation. So here u and v represent the object, distance, and image distance respectively from the mirror. And f is the focal length, and for concave mirror r is positive, and for convex mirror r is negative. The slope of the ray is always measured with respect to the forward direction of the travel. Therefore, the slope of the initial ray is x1 dash equals dx by dz. Or we can write x1 dash equals x1 by u, where x1 is the height of the ray. On the mirror, similarly, the slope of the reflected ray would be x2 dash equals minus x2 by v. Or x2 dash equals minus x1 by v, since x2 equals x1. Also, we have written x1 dash equals x1 by u, or from that we can write 1 by u equals x1 dash by x1. Similarly, we can write x2 dash equals minus x1 by v. Therefore, 1 by v equals minus x2 dash by x1. Then equation 7 becomes x1 dash by x1 plus minus x2 dash by x1 equals 2 by r, or we can write x1 dash minus x2 dash equals 2x1 by r. Right? Or from this we can write x2 dash equals x1 dash minus 2x1 by r. Let this be equation number 8. Equation 6 and 8 can be written using matrix for reflection. That is x2 dash equals 1 0 minus 2 by r 1 into x1 dash. By following matrix multiplication, we get the reflection matrix r equals 1 0 minus 2 by r 1. Let this be equation number 9. Also, determinant r equals 1 0 minus 2 by r 1, which is equal to 1. Let this be equation number 10. Thus, using reflection matrices and translation matrices, we can obtain the ray coordinates after any number of reflections and traversals by simply multiplying the matrices together. But it should be noted that the matrix multiplication must be done in correct order. So, let the coordinates of a ray be x1 and x1 dash in a plane which is at a distance d1 from a concave mirror of a radius r. Let the ray suffers a reflection at the mirror. Now we have to determine the coordinate of the ray in a plane at a distance d2 from the mirror. That is, we have to find the coordinates at the plane a2, b2, the coordinates of the ray on the mirror just before reflection, that is at P, will be on the mirror, that is at P, will be written as zeta 1 dash equals 1 D1 0 1 x1 dash. Here x1 and x1 dash are the coordinates, that is height and slope of the ray in the plane A1 B1. The coordinates of the ray just after reflection, that is at P but just after reflection, will be zeta 2 dash equals 1 0 minus 2 by r 1 into zeta 1 dash. So which is equal to 1 0 minus 2 by r 1, and substituting the values of matrix zeta 1 dash, which is written earlier, that is 1 D1 0 1 x1 dash. And finally, the coordinates of the ray on the plane at a distance d2 from the mirror will be x2 dash equals 1 d2 0 1 zeta 2 dash equals 1 d2 0 1 1 0 minus 2 by r 1 into 1 d1 0 1 into x1 dash. Hence, the matrix for the traversal from the plane A1 B1 to A2 B2 through a mirror will be represented as S equals 1 D2 0 1 1 0 minus 2 by r 1 1 d1 0 1. Thus the matrices for various operations appear in reverse order. So the matrix S is called as the system matrix. Between the planes A1 B1 and A2 B2, and in general we can write this matrix S equals A B C D. Also, the determinant of the product of the matrices is the product of the determinants, since determinant T equals 1 and determinant R equals 1. We obtain the condition for a system matrix S as determinant S equals AD minus BC, which is equal to 1. Now, let us consider a resonator bound by two concave mirrors of radii of curvatures R1 and R2 and are separated by a distance D. Let AB be a plane midway between the mirrors. A ray which starts from any plane AB towards mirror M1 after reflection from it travels towards M2. After suffering a second reflection at M2, it returns to the plane AB. This corresponds to one complete cycle of the ray, and this process repeats itself and we obtain ray traveling along both directions in between the mirrors M1 and M2. If the ray remains close to the axis even after arbitrary number of traversals, the resonator should be stable. When we impose the condition on the resonator system, we would obtain the stability condition. So let S equals ABCD. It represents the matrix for one complete traversal of a ray starting from a plane AB. Let the coordinates of the ray are x0 and x0 dash. When it started from the plane AB, then after one traversal, the coordinate of the ray x1, x1 dash equals s x0, x0 dash. So from this we can write x1, x1 dash equals system matrix, that is A, B, C, D, x0, x0 dash. Similarly, the coordinates of the ray after two traversals will be x2, x2 dash equals s x1, x1 dash. This is equal to A, B, C, D, A, B, C, D into x0, x0 dash. Or we can write x2 x2 dash equals A, B, C, D. As it appears two times, we can write it as square into x0, x0 dash. Hence the coordinates of the ray after incomplete traversals can be written as xn, xn dash equals A, B, C, D raised to n x0, x0 dash. That is equation number 14. For the resonator to be stable, the ray starting with coordinates x0, x0 dash should not diverge after n traversals. That's the coordinates are xn, xn dash even if n increases. To obtain the stability condition, we have to find out the value of s raised to n, where s is the system matrix, and to find its value we diagonalize the matrix. So in matrix U, diagonalize a matrix S if U inverse SU equals lambda 1 0 0 lambda 2 let this be equation number 15. Here U inverse is the inverse of matrix U. That is, we can write U inverse U equals U inverse, which is equal to I, where I is the identity matrix, and that is I equals 1 0 0 1, and lambda 1 and lambda 2 are called as the eigen values of the matrix S. To get S from equation 15, we pre-multiply equation 15 with U and post-multiply by U inverse. That is, S equals U lambda 1 0 0 lambda 2 U inverse. And on simplification, we get S raised to n equals U lambda 1 raised to n 0 0 lambda 2 raised to n U inverse. And on simplification, we get S raised to n equals U lambda 1 raised to n 0 0 lambda 2 raised to n U inverse. Let us be equation 17. To obtain lambda 1 and lambda 2, let us write an eigenvalue equation. A, B, C, D. Theta, eta equals lambda theta eta. Here the above equation is called as an eigenvalue equation and can be rewritten as A minus lambda B C D minus lambda theta eta equals 0. For a solution to exist, the determinant of this matrix must vanish. That is determinant A minus lambda B C D minus lambda equals 0. And on simplification we get A minus lambda into D minus lambda minus BC equals 0. That is lambda square minus lambda A plus D plus AD minus BC equals 0. But AD minus BC equals 1. That's from equation 13. Therefore, we can write lambda square minus lambda into A plus D plus 1 equals 0. And on simplification, we can say that this equation has two solutions, lambda 1 and lambda 2, where lambda 1 equals A plus D by 2 plus A plus D by 2 the whole square minus 1 is to 1 by 2, and lambda 2 equals A plus D by 2 minus A plus D by 2 the whole square minus 1 raised to 1 by 2. So these are the two eigenvalues of the system matrix S. And if you write cos theta equals A plus D by 2, then we can write lambda 1 equals cos theta plus I sin theta, which is equal to e raised to I theta, and lambda 2 equals cos theta minus I sin theta, which is equal to e raised to minus I theta. Also, we have written earlier that s raised to n equals u lambda 1 raised to n 0 lambda 2 raised to n u inverse, where lambda 1 and lambda 2 are given by this particular equation. It can be explained that if s raised to n should not diverge as n increases, theta must be real. Hence, cos theta and sin theta will be finite. Therefore, cos theta must be between minus 1 and plus 1, and that is minus 1 less than or equal to A plus D by 2 less than or equal to 1. So this is the next condition. This is the stability condition of the resonator system. So now let us consider a resonator system consisting of two mirrors of radii of curvatures R1 and R2 separated by a distance d. For a ray starting from the plane AB, The system matrix for one complete round trip would be S equals A, B, C, D. That is, it can be written as S equals A, B, C, D. That is, on simplification we get 1 minus D by R1 minus 3D by R2 plus 2D square by R1 R2, then minus 2 by R1 minus 2 by R2 plus 4D by R1 R2 minus D by 2 minus D square by 2R1 plus 1 minus D by R2 into 3D by 2 minus D square by R1 minus D by R1 plus 1 minus D by R2 do 1 minus 2D by R1. So let this be equation number 22. So comparing equation 22 with this equation, we get A equals 1 minus D by R1 minus 3D by R2 plus 2D square by R1 R2. And D equals 1 minus 3D by R1 minus D by R2 plus 2D square by R1 R2. Substituting the values of equation 23 and 24 in the expression minus 1 less than A plus D by 2 less than 1, we can write minus 1 less than or equal to 1 minus 2D by R1 minus 2D by R2 plus 2D square by R1 R2 less than or equal to 1, or we can write 0 less than or equal to 1 minus D by R1 into 1 minus D by R2 less than or equal to 1, which is the stability condition. Thus, for a resonator to be stable, R1, R2 and D must satisfy this equation above equation 25. Here this figure represents the stability diagram, and from the figure the shaded region corresponds to stable resonator configuration, and the origin, and here the origin corresponds to the confocal resonator. The figure also shows that the various resonator configurations. So we can say that a resonator formed by two converging mirrors may become unstable if the power of the mirrors is too large. Also, a combination of a concave and a convex mirror may still form a stable resonator configuration. That's all. Thank you.